Okay, so let me start as usual with a brief reminder what happened last time. So we introduced some spaces, and the notation was M20T for the square integrable martingales. So martingales. And then it was the space M2 star. Well, I have an idea to use two different colors today for two different setups. Maybe it's wrong, but let me try. Okay, it's going to be green. And this M2 star is nothing but the limit of M20T. So this is the set of processes on the half line such that M is M20T for any T. And then let me also from the very beginning introduce actually a more general class which we already saw. This is the class of all local martingales. So this is, okay, if it's the same, gosh. Oh. So this is a more general class. And then there were spaces L2 0Tm. This was for M from here. Well, from here. Is the space of all processes adapted, progressive, better to say, such that the expectation of this integral is finite, right? And then it was the space in a similar manner defined, which I suppose to be green, so I'm not very good with colors, but okay. This with star, I mean, I still have a sort of a resort in the notation. So this L2 star M was, again, similar limit. And let me also from the very beginning for today introduce the space L2 log M, which by definition is the space of all processes, again progressive, such that, oh, this is the definition, such that this integral is finite, almost sure. Okay. So this is a larger class. So here the integral should be in L1. And here I just ask that, okay, pathwise, it is in a sense well defined. Okay, so and then what happened? So for a simple process H, so if H was a simple process, which means this is basically the step function. Let me put j minus 1 here. J minus m, j minus 1. It's measurable. There is a straightforward notion of the integral h with respect to m. So this is the same notation as that, right? So I use them somehow in parallel. This is always the same. I mean, and this is just the notation. Okay, to define this, you just integrate the step function, and what you see, oops, this is a mess, right? This is not a step function. Sorry for this. Step function is that, and when you integrate it, what you see is this process. Okay, so then it was a claim that this mapping H to M can be completed by isometry to spaces L2 star and M2 star. Isometry from L2 star, M to M2 star. Okay. It was some amount of work to be done to prove that spaces are complete, but basically it was a simple check that, okay, it works on step processes, and then okay, it paves us a way to define it for L2 functions. So, good. Just a small remark still here to save space. If we do not know that our martingale is square summable, then we have some troubles with this definition. Why? Just because when we compute H2 norms, L2 norms here, we see that for step functions they are infinite. Is it clear? I mean, so it was some computation behind last time, and it was basically computing. Okay, what is this and what is that for this H and this H dot M, and this computation basically led us to integrals of this quadratic variation of M, and I mean along segments. And if this quadratic variation of M is infinite, okay, we're in some trouble. So remark, if M is not there, then there are some troubles with step functions. Okay, good. And then it was a proposition which says, okay, this was going to write in green, but I lost the green chalk. Okay, let's try. So, if M is and H to start M has continuous trajectories, then one can think about this definition just in a very natural way, meaning that for any sequence of nested partitions, if you just compute Riemann sums this way, probably Pn HTJ minus 1n and TJn, then this converges to the stochastic integral, in probability. And if you do the same with squares, then what you get is the integral with squared, is the integral with respect to the quadratic variation. Now, what do I mean by writing this in green? Right now, we just have no definition of the object on the right-hand side of the limit in any other case. Okay? But later, I will not discuss this in full details, but later, basically, all these assumptions, I mean, in the construction, will be withdrawn in a sense, and the real spaces with which one, at least, can work are yellow ones. Okay? So, right now, we just have no definition for the stochastic integral if we are in the yellow setup. Okay, good. So what is the proof? It shouldn't be very hard. So first, consider bounded case. So let first H is bounded for any S0t for any omega. Then just note that if I introduce a step process if I introduce the step process, say HSM, which is by definition just the sum for G1 to by n H minus indicator. So I take my process H and I approximate it by step functions. So that's fairly standard. So if I introduce such a process, then what is written on the left is nothing but the stochastic integral of this Hn with respect to n. So this is exactly the definition which is here. Okay, so and then we have, by this isometry, by this idea, we have that the expectation of this squared. So this is just the expectation of the difference of the right-hand side and the left-hand side in A is equal to the expectation of the integral Hs minus Hsm squared dm. What's written is this isometry. And then I say, okay, I know this tends to 0 as n tends to infinity. Pointwise, I mean, for any given S, I mean, almost surely in both S and omega. Because I know that my trajectories are continuous almost surely, and this difference, okay, what's that? This is Hs minus H evaluated at some nearby time. Okay, so the picture, okay, I hope it's clear. And then if I know that everything is bounded, then I just apply dominated convergence. By dominated convergence. In particular, I know that this tends to 0 in probability. okay, because I know that the expectation tends to 0. And if I do not have general, if I do not have this boundedness assumption, what I do is again very standard. I just introduce, let omega k be this subset of the probability space such that H is in fact bounded by k. As all the trajectories are continuous, I know that these subsets they exhaust the whole probability space. So it means, okay, for any epsilon there is k such that the probability of omega k is almost 1. And then on this set, okay, then the idea is to consider instead of the process Hs something which is bounded. I mean, just, okay, Hs is say equal to Hs k, not a good notation, okay, Hs tilde, where, okay, let me just write this way, Hs mean tau k, where k is a stop in time, the first time the process crosses the level k. And then what I say is that, okay, I can apply what's written above to this process. And so on the set omega k, I know that there is a convergence. And the rest has small probability. Yep. So this proves A. And for B, okay, this is some reasoning, not very hard too. So what's B? To prove B, I just say, okay, let me write something that reminds what is here on the left, but not exactly equals. So let me, for two integers k and n, so the picture is that we have two partitions, they are nested. So say here, this is the partition T j minus 1 k T j k. And inside, there is a finer partition like that, T minus 1 n T I n. And for a given index I will use the notation j of I, similarly to the construction of the quadratic variation. So, okay, this j, noted ji. So it means that the nested segment, I mean the segment of the nested partition, is contained in this particular segment of the Rutherford partition. Okay, so then what I write is such a sum. So here it's k. But then I sum over all I with j of I j these increments. T I n minus n. N squared. So what happened in this left-hand side, I have replaced ht, Okay, this is the mass with ij, hti minus 1n by htj minus 1. Okay. Okay. So instead of taking the value of the process here, now I'm taking the value of the process here. Okay, just some intermediary object. And what do I know? I know that if I now, this is of course for n greater than k. I know that if I send n to infinity, then on each of these orange segments, or red, okay, these orange, okay, line, these orange segments, this orange partition is fixed. So, and on each of them, I'm just summing the squared increments of the martingale. So what I know is that for a fixed k and n tends to infinity, this converges to hj minus 1k increment of quadratic variations. Tj k minus n. This is just the convergence of quadratic variations in probability. Okay? And, okay, now here, if I now send k to infinity, then what I see is just a definition of Stieltjes integral. So the next step is to say that if I now send k to infinity, then this converges to the integral hs dns. Actually, almost surely. Okay. Now, what do I say? I just say, okay, for a given. Okay, let us keep it. I mean, and at some point we should choose all the parameters carefully. So let us just keep it on the blackboard. But essentially what I have is that this sum, I mean, if I handle n and k properly, then this sum is close to the integral. Okay. And now what is the difference of this sum? I mean, this is not exactly what I need, what I need here. So what is the error? What I'm saying is that, okay, this is essentially the difference between this and that. So in any case, this is less than, let it be w, not omega h epsilon k by the sum of increments squared and what's that? This is modulus of continuity of H, and this is the mesh of the partitions, of the partition 0 of the partition number k. So what I'm saying is that these factors are exactly the same, so the only difference is here. And what I know is that the difference between orange and yellow points is less than epsilon k. And also what I know is that this converges again in probability as n tends to infinity to this by the quadratic variation. And also what I know is that when I then send k to infinity, then surely this converges to 0. Because trajectories are continuous. Okay, hopefully this is enough to cook up the proof. So now what do you do? Now given epsilon, find k such that first, okay, let me put something. Okay, such that first here the difference is less than epsilon with probability at least 1 minus epsilon. And here, say that okay, that the whole guy is less than epsilon. Okay, such that the probability of this being greater than epsilon is less than 1 minus epsilon. And similarly for the first line, in the first line. And then for this k, then find n capital, which depends on this k and epsilon, such that in the first convergences and this inequality, the probability that the difference is at least epsilon is less than epsilon. Sorry for this informal writing. So first adjust k, to be on the safe side here, and then given that k, adjust n to be on the safe side in the first inequalities. And then altogether, so what you conclude is that for any small n greater than this n capital, the probability of the event that what we need differs from this LTS integral by more than for epsilon is less than for okay, there is no 1 minus here. Okay, this is the bad event. The probability of the bad event should be small. Less than well, there is almost nothing here besides this trick to introduce such an intermediate sum and the careful choice of the order what should be big and what should be, what should be chosen first and what should be chosen second. So, are there any questions on this slightly technical part? Well, if no, then the next paragraph, let me start it here. This is called Semimartingales and Ito formula. Okay, so what is the sort of a perspective? What have we constructed until now? So we know how to integrate with respect to square summable martingales. We know how to integrate with respect to finite variation processes. Okay, so for the first, this is a sort of this is some construction, and for the second, this is just still TS integral. Okay, so definition: a process X adapted with continuous trajectories, as usual, is called semi-martingale if it can be written as a sum of what is called the martingale part and the bounded variation part, with where okay, now I need colors, where as a sort of a, you know, of a downgraded version of the whole theory, you can consider just martingales from the space M to star. But more generally, just a local martingale. And A is a bounded variation process. And remark, this decomposition is unique if it exists because we had some lemma. It is impossible for a local martingale to be a bounded variation process at the same time. Okay. Now, what do I need? What other definitions do I need for them? Sorry for this strange choice of space, and so I'm going to consider. Oh, la la. Yes, I'm not a proper Swiss professor. Okay, I'm going to continue there. So for a semi-martingale, just define this sign of quadratic variation to be the quadratic variation of the martingale part. Okay, this is just a definition. And if I have some progressive process, then this hxt I just define to be, okay, in some cases I know how to integrate with respect M, and I always know how to integrate with respect A. So I just define it to be the integral with respect to the martingale part plus the integral with respect to the bounded variation part. And now some discussion. So what do we need for this object to be well defined? So here we need that this is finite almost surely, right? because this is a pathwise definition. I mean, there is nothing deep here. I mean, I just take a sample of A, a sample of H, and if this is finite, I can define the value of the Celsius integral. So here, again, there are two options. So the first option that we already know how to treat is the option in green. So we know it works if M is in M2 star and H is in L2 star M. Again, I prefer to say it right here. So more generally, there is a way to define this stochastic integral if M is just a local martingale and H is L2 log M. And definitions are here. So I mean L2 log, we do not have any summability assumption for, I mean, in omega. So we have L2 in time, but we do not assume anything in omega. And the yellow part for now is, just some saying. I'm telling you, okay, that there is some better life, okay, in a better yellow life. This is a more general definition. Okay, and so these are just definitions, and just yet another remark in words. Here, even in case M is a very good martingale, say the Brownian motion, I mean, if it is in fact square summable itself, still this space is not equal to that space, right? Because it might happen that the process H is almost surely continuous, so this is a very nice process, but with reasonable probability it blows up very fast. So that, okay, this integral on a set of reasonable probability is really big. And so you cannot guarantee what you can guarantee that this integral is finite. Okay, good. So then what I also need before formulating the very central theorem and the whole story, the ethos formula. So let me start with some preliminary lemma, which is actually, I mean, it's already done. I mean, there is, I mean, at least in the green setup, there is nothing to do. So what does it say? It says that if, again, let me write it in green. Okay, yeah. We're going to the better life, so I'm losing green chalk. So if I can write it in white now. So if X is a semi-martingale, I have a nice option. So I just do not specify which definition I take here. So if this is a semi-martingale and H has continuous trajectories, then for any sequence of nested partitions, if I just write exactly the same as here, but with X, Tj minus 1, and then this converges in probability to what it should, to the X. And if I do the same with squares. Then it converges to, again, the same. And remember that just by definition, this is the quadratic variation of the martingale part. And the proof, okay, we can do the proof at the moment only in the green setup, right? Because in the yellow setup, we do not know how to define this object. In the green setup, well, you just say, okay, A is already done because it follows, remember, this is nothing but the sum of the stochastic integral and LTS integral, and it holds separately for each of the components. A holds for both martingale and finite variation. And B, still you decompose X into M and A. Then there is a term which is the square M minus the increment of M squared, and it converges to what we need. So the only issue is to prove that all the other terms do not contribute. So for instance, if you take the cross term, then okay, you just say what should I say? Let me just bound it this way, just the maximum of H. I mean, it should be trivial bound. Maximum of H on this segment, so H has continuous trajectories. And here I write this modulus of continuity. Okay, and here I have a sum of increments, so this is less than the total variation. Like that. And then I say, okay, this is finite almost surely, this is finite almost surely, and this converges to 0 almost surely. Okay, so this converges to 0. And in particular in probability. So the reason here is that if you have a right, if somebody gives you a right to sum these increments, which is exactly the property of a process to be of finite variation, right? The sum of just simple increments is finite. Then there is nothing to do because you can use a trivial stupid bound for everything else. Okay? I mean, that's the deep reason, I mean. So, and bless you, and the conclusion of that cross terms do not contribute. I mean, that's the bottom line. Okay? Are there any questions so far? So again, what happened? I introduced some class of processes, which is called class of Semimartingales. And then I said, okay, I have just formally defined integration with respect to such processes. Then there is this technical lemma. And now I'm going to, just before the break, just formulate the eta theorem. So where should I do it? Maybe here. So, okay, now the central theorem of everything. So, it must have a number 42 if there is some enumeration. Okay, let xt be a vector valued process in Rn okay, T, okay, as usual, this is the process on the half line, and all these components are semi-martingales. Let f be a C2 function, meaning twice continuously differentiable. In fact, I do not assume a priori that derivatives are bounded. So this is C2 on a non-compact space. Then this is like Newton-Leibniz formula. So I ask, what is the increment of f of x over some period, some amount of time? The answer is, okay, like in the Newton-Leibniz, you should integrate derivatives. So what's that? This is the stochastic integral. So this is my process H. This is my semi-martingale. That's not it. Plus some other terms with second derivatives. And what's that? This is my stochastic process, and this is a finite variation process. Okay, this is the bracket of two local martingales. Okay, so this is stochastic integral. This is finite variation. With some comment. And the comment is, provided we have a right provided we have a definition of the right-hand side. Okay, there are basically two cases. If we're in the green setup, with the second term, there is no problem. So this is the integral with respect to the finite variation process. It is always defined. In fact, it might be some problem it might be some problem here, right? Why? Because, okay, I said that I do not assume in general anything about these derivatives. And it might happen that if I work in the class of square summable martingales, that I lose integrability assumption here. So, okay, the comment is that in green, if martingale parts of xtk, it was k, km, of course. So if martingale parts of the semi-martingales are in M2 star, and the only definition we have is a definition developed last time, and we only know how to define this integral for h in L2 star, then you need some assumptions on the function. Some ability. Because a priori, this guy might not be well defined. And the example is, it was already mentioned during the previous lecture, or the last but the previous. The example is, for instance, when you take the Brownian motion in 3D, and this function you apply is just 1 over the absolute value of bt. So what you have is not a martingale, and a posteriori it means that, I mean, formally speaking, we had no right, I mean, with our construction to apply this formula. Because we know that in the green setup, this procedure, this stochastic integration, it starts with some martingale from here, with some h from there, and the result is again there. So the result is always a true martingale. Okay. In yellow, I mean, in general, it works for, I mean, for all semi-martingales, and then there is no assumptions, with no assumptions. No. So, okay, let us make a break. Say 10 minutes. I'm sorry for being late. But somehow I prefer to write on the blackboard, so you have some time to digest what's going on. There are two different setups, and somehow we develop them. I mean, I explain both of them in parallel. Okay? So, yeah, 10 minutes break. Well, let us continue. So what is the plan with the proof of this formula? In the green setup, almost everything is already done. So, I mean, that's fairly simple, and I'm going to prove. And then I'm going to discuss how to define objects in the yellow setup. But I'm not going into details. I mean, so I'll just explain how one can define such a stochastic integral. I mean, what is a proper way. But I'm not going to deduce everything rigorously, I mean, for this formula. Nevertheless, of course, I'm going to use it in full generality afterwards. Okay, so proof. And again, I mean, rigorously what we can do right now is only the green case. And again, just to simplify what's going on, I'm going to treat the case n equals 1. I mean, the general case is for exercise. Eventually, this is about the Taylor's formula. I mean, Taylor's formula works well in any dimension, so there is nothing to here. So we consider so what I then mean by summability assumptions, I mean that for some reason I know this process is an L2 of that in L2 star. For instance, it might happen that derivatives are bounded. Okay, if just derivatives of f are bounded, then I have no problems with summability. It might happen that I know some additional information like x is the Brownian motion and I know it grows polynomially in, or even exponentially in B. I know that again, still there is summability. So I just take it for granted, and the proof is based on this lemma. I mean, it's already here. So the idea is that if I know this statement, that I'm already done. Then I'm already done. So okay, what do? I just take some partition. And write f xt minus fx naught as a sum of increments okay, this is trivial, and then apply Taylor's for each of the increments. On the left, I mean, with the base point on the left. So here, this is derivative by the increment. Then second derivative by the increment squared. And then there is some correction. And I write the correction in the following way. Okay, I could write this identity exactly if I replace the left end of the segment by some intermediate point here, some unknown intermediate point. Right, so what I do, I just say, okay, here is something like that by the increment squared. By the increment squared. Right? There's just an identity where size, okay, they are random. I mean, for any given sample, I just apply Taylor's formula. Okay. And then I say, this lemma tells me that the first sum tends in probability to this stochastic integral. The second tends in probability to this still TS integral. So the only remaining thing to be done is to prove that this tends to 0. And again, what you do, you just say, okay, let me bound it, I mean, for this let me bound it in a stupid way, just saying this is less than the modulus of continuity of this with epsilon n, right? By the quadratic, I mean by the sum, not the quadratic variation, but by the sum of the increment squared. And that is exactly the same reasoning. I know that this tends to 0 as n tends to infinity almost surely, and I know that this is bounded. So effectively what I'm saying is that everything is already done before, is already done here. Okay, so what do we use? We use, I mean, what is the, somehow there are two remarkable things about this formula. First is that there is a second term, right? I mean, this is something which is absent in the classical setup. Second remarkable thing is that there are no other terms. Okay, if there is a second, why there is no third, etc. The reason for that is basically here, is that the sum of increments squared is always finite. And coming one step back, the reason for this is exactly the existence of quadratic variation for local martingales. Remember, it was a quite technical theorem, right? I computed something on this blackboard. It was blah, blah, blah. But this is exactly the reason why, why this terminates.
Excuse me? Don't we need uniform continuity of second derivative?
No, just because I apply it pathwise. I mean, I take a sample of my process. And for this sample, this is a continuous function. I mean, it's well defined on a segment. On the segment 0t. Okay, it's uniformly continuous on this segment. I'm not sure it was your question. No. No. And there. And the convergence here everywhere is in probability. Okay. Good. So then, and you see basically if you are in higher dimension, okay, you write multidimensional Taylor formula, and this is exactly the same reason. Okay, then some discussion, as I promised, of the bright yellow life. So how to define discussion. How to define this mapping from H to H and T for just local martingales and H just local L2. Question mark. Again, so let us perform some computation with in a nice setup with step processes and square integrable martingales, just some computation. Okay, let as usual M is an M2, say star. H is two-step process. And M and HM is this. Let us take another square summable martingale. What I would like to do, so what I know that this is, it was in L2 star, so this is again in M2 star. HMT, thanks. And now I realized that it was some mess in the reminder, right? Okay, so I forgot to put here H or something like that in the reminder. So let us take another martingale and compute the quadratic variation, not the quadratic variation, the bracket of H dot M and M. So essentially, remember, so it was about the quadratic variation, that this is the limit of what? Of such sums of increments squared. But this is a bilinear form, so the same statement holds for the bracket. So what I claim is that effectively what you do, you just compute the bracket of M and N, take the increment over the segments and add them with C. Formally, you can think about linearity of this form, so you just do the computation with each of the terms. Okay? So this is just the formula. And what is on the right? On the right, this is the integral of HS d mn. It's still just integral. Okay. Yeah, this is just a simple computation. And then there is a claim that actually for any H in L2 star M, there exists unique process H dot M in M2 such that for any other martingale M2, this holds. So the moral is that you can use this property as a definition if needed. Okay, so here is the identity. The crucial identity. Okay, some comments. I mean, what should be done? First, uniqueness is basically easy because if you have two candidates for this identity, then you just subtract one from another. So what you have is that the first candidate minus the second candidate has a zero bracket with any other local martingale. In particular with this difference itself. So uniqueness you just write that, okay, if I had two candidates, then this bracket must be 0, which means the quadratic variation of a local martingale is 0, the martingale is 0. So uniqueness is an easy statement. Existence, okay, some work to be done. By the way, even when I wrote this, it is not totally safe, because why do I know that the right-hand side is well defined? I knew that H is in L2 with respect to M, but now what I claim is, okay, it is in L1 with respect not to MM, but to some other bracket. So, okay, this is a sort of Cauchy-Schwarz inequality, which is called, well, as I forgot, Watanabe and Kunita, probably, yes? Yes, am I right? If anybody knows, yeah, Kunita. Which basically says that you can write, given H, which is in L2 with respect to M, and K, which is in L2 with respect to N, you can write this sort of an analog of Cauchy-Schwarz. Okay, this is not very hard, but still some work to be done. And just to define the right-hand side. Okay? Then you say, and this holds, almost surely this holds pathwise. So, and then you say, okay, this is well defined. Just put here k equals to 1. Okay, and then once this is done, you can just say, okay, I now would like to use it as a definition in the general case. So, in the general case, now you prove, okay, claim that for any M just local martingale, for any H which is in local L2, there exists unique HM again in local L2 such that, okay, what? Such that this holds. Such that this condition is fulfilled for any local martingale. I mean, to formulate it, you do not need to know anything, right? So we know that the quadratic variation and the bracket then is well defined for any local martingale. So this is exactly the condition which you can use. And just a sort of a glimpse of how you prove it, you localize everything. I mean, here you just consider stopping times. I mean, instead of H, M, and N, you just make them true martingales considering stopping time and then pass to the limits. So this identity, it does not involve any expectations. So this is a sort of an advantage, right? So this is something that you need to prove pathwise. So this is the construction. And then you say, okay, everything I told you before actually works in this case too. Are there any questions? Okay, good. So yet again, just the bottom line. There are two setups, the green and the yellow. In the green setup, what we work with are square integrable martingales. And the processes H are in L2 star of M. Then there is this procedure of stochastic integration, which again returns us the martingales from square integrable martingales. So this is a closed class under operation of stochastic integration. There is a more general yellow setup when we work with local martingales and this space L2 log. And again, this procedure of stochastic integration returns us the same space L2 log. What is the advantage of the yellow setup? The advantage of the yellow setup is that in the Ito calculus, we just do not care about any summability of this guy. Okay? If this is a continuous function, this is already okay to be in L2 log. So L2 log is just L2 in time. If your function is continuous on a given sample, that's okay. So, all right, so we developed this, and now we just benefit from what we have. So now the set of basic examples to see how easy the life actually is. I don't need this anymore. So, examples. Now let me start with a remark. So, remark, people typically use differential notation instead of this just because it's shorter. I mean, it does not mean anything, but you know, it's easy to write things. So just introduce differential notation. df xt is sum df over, okay, it was k, and dxk k plus sum 1/2. Okay, by definition, this means exactly that. They are not differential forms, I'm sorry. Okay, so then example 1. So this is the formula integration by parts. What you do, you just take two semi-martingales, x and y, and the function f, which is the product. Just note that if we're in the green setup, it might be some issue here with some mobility. I mean, in general, for some general semi-martingales. So, okay. What should I do? I should first differentiate this in x. Okay, maybe let me even write this way to be consistent. So I should differentiate this function in x1. Then in x2, and then in both. So what I have is the quadratic variation. Not quadratic variation, the bracket of these two. There is no 1/2. Is it clear what happened? I mean, why there are no other terms? This is the function x1, x2. If I differentiate twice in x1, this is 0. And then there are two terms, k1 and m2, and vice versa. Okay? In particular, so you can plug into bt, and what you have is the formula for dbt squared. We started the whole construction with. Okay, then we have a one-dimensional process which is constructed from the Brownian motion. Right here, sigma s. It might be something that does not depend on the probability space. It might be some predictable process, whatever. I mean, some progressive process, say with continuous paths adapted, plus a ds. Okay. Again, in differential form, it means this is exactly the same. I mean, by my notation, as to say dx sigma s dbs plus a ds. Okay, good. And now I ask what is the expression for f of xt. So what is d of xt? Okay, I have only one variable. I just apply my rule. This is f prime dxt plus f2 prime xt over 2 quadratic variation. The question is, okay, what is the quadratic variation of this process? So okay, it's written here. I'm going to claim that this is actually sigma squared dt. Why do I know this? For instance, I know this from here. So imagine that here I take whatever, sigma b, and I apply this rule. So what this rule tells me, it tells me that I can just take this factor and put it out from the quadratic variation. Okay? What I'm saying is that this is actually sigma t squared d bt. And so what we have is f prime xt sigma, it should be sigma t dbt, sorry. Oh, and should be t there as well. Oh, why nobody told me? I mean, I'm so sorry. It should be, of course, the same variable there. T dt. And here, okay, this is sigma dB plus there are two terms in front of the dt. Okay, just a decomposition of this process. Some comment which is very simple but still deserves to be done. I mean, in this decomposition, remember the class of processes we are working with is a sum of martingales, whatever, summable or local, and finite variation processes. Okay? In all these decompositions, this, I mean, the stochastic integral of that is a martingale part, by definition of a stochastic integral with respect to the martingale dBt. And this is a finite variation process. I mean, okay, maybe here. So this is martingale part. This is bounded variation. In particular, if I just ask what is the condition for this fxt be a local martingale, the condition is that this is 0. Okay? Because, I mean, in this formalism, it's already, I mean, everything is already written in the form split into martingale part and bounded variation part. Good. Then, yet another example. Remember that as a sort of a link between the first part on the Brownian motion and this part of stochastic calculus, I used harmonic functions. And it was some discussion that it seems that if I take any harmonic function of the n-dimensional Brownian motion, then h of bt is a martingale. For sure, this machinery allows us to check it basically immediately. So let h be harmonic. Then, if I compute if I would like to write the value h blah 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 as a stochastic integral like in the Ito's formula, so what I need is to compute this. So, okay, this is a sum of dh xk dbtk plus 1/2 sum over km there is nothing deep. This is 0 if they're different. This is dt if k equals m. Then what you have is the Laplacian. It cancels out. So there is only the martingale part, and we are done. This is indeed a local martingale. And now, sort of a remark. Well, one can consider harmonic functions in the whole space. But this is not very convenient, I mean, to have such a restriction. So, for instance, imagine that this function is defined in some smaller domain. For instance, just Rn minus 1 point. It should be fine for us because we know, or at least it's somewhere in the homework, that the Brownian motion does not hit a given point. Never. I mean, so if it started not at the origin, it never hits it. And if it started there, it escapes immediately and never comes back exactly to this point. So it should be some way to adapt everything to this setup. And indeed, this is just very technical. So imagine that we have, say, this, and okay, let it be f, and from somewhere we know that xt in u for all t almost sure. The message is that we still have a right to apply Ito's formula and Ito's calculus. Why? Okay, here is our domain U. Just consider a smaller open set V. Which is strictly inside. And then construct, let TV be the stopping time, be the increment of all times we are not in V. We exit it. So our trajectories are something like that. They are always in U, but they can exit V. And construct function fv defined in the whole space that agrees with f on this set. This is something from real analysis. This is always possible. So if you have a smooth function here on the open set, then if you shrink it a bit, you can always prolongate, extend the function to the to some smooth function on the whole space, and then apply eta to fv xt. It's tau, right? Tau v. Instead of f. And then pass to the limit when v fills the whole U. So what is the message? The message is that, in fact, I asked there that my function is C2 in the whole space. But of course, this is just technicality. I mean, if I know by some reason that my process stays in some open set, and I know that the function is C2 on this open set, that's fine. I mean, I can apply eta calculus. Okay, good. And let me then start the next paragraph just to formulate a very important result. And after that, we continue next time. So, notice. So actually there are several results, and I'm going to group them all together to here. There is another theorem which is not quite sure was the correct pronunciation. I think Dubin's, but yeah, as I said, Dubin's-Schwarz. I'm not quite sure. And conformal invariance of the two-dimensional Brownian motion. It's basically altogether about the same thing. So what is the characterization theorem? Actually, I already mentioned it when started the discussion of the stochastic integral of martingales for the Brownian motion. So remember, it was a martingale b squared minus t. And I mentioned that actually this is enough to know, I mean, that if we have a process and we ask how can we know this is a Brownian motion, it's enough to know only two martingales. So that's exactly what Levy's theorem says. Let this be a vector valued process, moreover local martingale with continuous trajectories as usual. The claim is that if we know that the quadratic variation, that the bracket xk, xm is 0 for different indices and t for k equals to m. Remember, what is this process? This is the unique process, just a reminder. This is the unique process such that this product minus the process is a martingale, right? So basically, to know the quadratic variation is exactly to know that this square, say in dimension 1, xt squared minus t is a local martingale. So, this reminder. Then xt is n-dimensional Brownian motion. And as usual, there is no big difference between that one-dimensional case and the general n. So just think in dimension 1. In dimension 1, what it claims is that if I have a process which is a local martingale, and I know that x squared minus t is a local martingale too, then it's enough to conclude that the process is a Brownian motion. I do not need to know anything in higher orders, and the reason for this is basically exactly the fact that in the eta calculus there is only the second term. There is nothing more. Okay, very last comment. So it's going to be a new exercise sheet. This is really important. I mean, a sort of an advice. It's really important to understand what's going there because this is about eta calculus. Some questions compute this, compute that. You know, if you would like to continue, you need to have, I mean, in the next term, you need to have a working knowledge how to compute things like that. There is nothing deep here, just some language. But okay, just insist on this. Okay, are there any questions?
Is it possible to have this situation without continuous trajectories? Like the quadratic variation is t, but the trajectories are not. between, like, does after the quadratic variation kind of goes to zero?
Well, that's already, I mean,
Because if there were
I see what you mean. Well, okay, it depends. Somehow it depends on what you mean by the quadratic variation. So if you mean that we can define the quadratic variation, then what you are saying, okay, it tends to 0. If you just mean that I know that the process x squared minus t is a martingale, so what was the purpose of this reminder? It was just to say, okay, this saying is equivalent to saying that these guys are local martingales. Okay? If you just have this, then you cannot guarantee you have no jump, right? Because it might be that there is a jump, but the probability is just small. I mean, so if you know that this is a local martingale, there is no argument saying, okay, t is small, because of this there are no jumps. Right? Because it might be a jump, but with a small probability. Well, just, okay, what does it basically say? It says that the expectation of x1 squared is 1. It means that you cannot have a jump of order really bigger than 1 with a reasonable probability in amount of time 1. Okay, that's good, but you might have smaller jumps. So the answer is, I mean, in this setup, the answer is no. And then this is the question of how you define quadratic variation. I mean, so that's more to your original reason. Okay.